Nazi officers never knew the Allies had PLUTO pipelines pumping fuel. Under the Channel, dawn broke over the cliffs of Dover on that chilly morning in August 1944, revealing a strange sight to any observant watcher. A massive drum, 30 feet in diameter and weighing over 250 tons, was being slowly towed into the English Channel by 3 sturdy tugboats. To the casual observer, it might have appeared to be some peculiar piece of maritime equipment, perhaps a new defensive measure against German U-boats. To the Nazi intelligence officers, who may have spotted it from across the Channel, it seemed an oddity unworthy of serious attention. None of them could have imagined they were witnessing one of the greatest engineering feats and best-kept secrets of World War II, Operation PLUTO, a daring underwater pipeline system that would help fuel the Allied advance across Europe right under their noses. Before we dive into this extraordinary story, tell me in the comments, which city are you watching from? It's incredible to see our historical community spread across the world. And if you're new here, subscribe to the channel and turn on notifications. Each subscription helps us continue unearthing these fascinating stories that shaped our world. Now, let's get to the story. The problem facing the Allies after D-Day was as simple as it was daunting: fuel. Modern warfare runs on petroleum. Every tank, truck, jeep, and aircraft demanded a constant supply of fuel to maintain the momentum of the Allied advance into Nazi-occupied Europe. Military strategists estimated that petroleum products would constitute more than 60% of the total weight of supplies required by the invasion forces. Without reliable fuel delivery, the entire liberation of Europe could stall, allowing German forces valuable time to regroup and counterattack. The traditional solution, shipping fuel in tankers across the Channel, posed significant risks. These vessels were vulnerable to Luftwaffe attacks, U-boat strikes, and the unpredictable weather of the English Channel. Even if the tankers reached the French coast, they still needed to be unloaded into exposed storage tanks, creating further opportunities for German air raids to devastate the precious fuel supply. The Germans were painfully aware of this vulnerability. The Nazi High Command had devoted significant resources to attacking Allied supply lines throughout the war. Their wolf packs of U-boats had hunted oil tankers in the Atlantic with devastating effect during the early years of the conflict, and their intelligence services maintained constant surveillance of shipping movements in the Channel. Field Marshal Erwin Rommel, tasked with defending the Atlantic Wall against invasion, had emphasized the importance of denying the Allies a foothold by targeting their supply lines. If the invaders could be contained on the beaches, cut off from fuel and ammunition, their superior numbers would count for nothing. This concern over fuel supplies was not unique to the Western Front. The entire war had demonstrated the critical importance of petroleum in modern combat. Hitler had divided his forces in southern Russia in 1943 in an attempt to seize the Soviet oil fields in the Caucasus. Japan had attacked Pearl Harbor in part to secure access to the oil resources of the Dutch East Indies. Across every theater of the global conflict, military planners recognized that without fuel, the most powerful armies in the world could grind to a halt, rendering tanks and planes little more than expensive, immobile monuments to thwarted ambitions. In April 1942, as Allied planners were beginning to contemplate the eventual invasion of Europe, Lord Louis Mountbatten, Chief of Combined Operations, approached Geoffrey Lloyd, the British minister in charge of petroleum warfare. Mountbatten posed a seemingly impossible question. Could they lay an oil pipeline across the bottom of the English Channel? Lloyd didn't dismiss the audacious idea outright. Instead, he presented the challenge to his engineering consultants. The initial response was skepticism. No pipeline of this scale had ever been attempted beneath the sea. The logistics seemed overwhelming. How could they manage the enormous bulk of pipe required to span over 30 miles of channel? How would they connect sections on the ocean floor? And how would they contend with the channel's powerful currents and tides? The man who would transform this fantasy into reality was Arthur Hartley, chief engineer of the Anglo-Iranian Oil Company, later to become BP. Where others saw insurmountable obstacles, Hartley saw possibilities. He had a spark of insight. Perhaps they could adapt existing submarine telegraph cable technology. Instead of carrying electrical signals, the cables would transport fuel. It was this creative leap, repurposing one technology to serve an entirely different function, that would form the foundation of Operation PLUTO. Hartley wasn't working in a vacuum. Britain's desperate wartime situation had fostered a remarkable environment of innovation across all sectors of society. Scientists, engineers, and inventors were given unprecedented freedom to pursue unconventional solutions to wartime problems. From the development of radar to detect incoming enemy aircraft to the creation of artificial harbors for the D-Day landings, British ingenuity was in full bloom. PLUTO would be yet another example of this innovative spirit, a testament to the creativity born of necessity. The project was given the innocuous code name PLUTO, an acronym for Pipeline Under the Ocean, or sometimes Pipeline Underwater Transportation of Oil. The name cleverly masked the true purpose while giving a wink to Disney's famous cartoon dog. This seemingly playful designation was just one of many deceptive measures employed to keep the operation hidden from Nazi intelligence. The entire project was classified at the highest levels, with staff given strict instructions never to use the words Petroleum Warfare Department, or even its initials in any correspondence. Locations were literally erased from maps, and drivers making deliveries to PLUTO installations had to call from public phone booths for directions rather than carrying any written instructions. Winston Churchill, Britain's indomitable Prime Minister, took a personal interest in the PLUTO project. He recognized its potential strategic importance and ensured it received the necessary resources despite competing wartime demands. In his characteristic style, Churchill is said to have remarked upon being briefed about the underwater pipeline concept, "This is not a time for business as usual, but for business as unusual." The Prime Minister's support proved crucial in overcoming bureaucratic obstacles and to securing cooperation from various government departments and private companies. The technical challenges were formidable. 2 different pipeline designs were developed, each with its own strengths and weaknesses. The first was known as HAS, named after its developers, Hartley, Anglo-Iranian, and Siemens. This pipeline consisted of a 3-inch lead tube core wrapped in multiple protective layers: asphalt, paper soaked in vinylite resin, steel tape for strength and flexibility, jute tape, more asphalt-impregnated paper, and finally a protective outer armor of 50 galvanized steel wires. The entire assembly was then covered with camouflaged canvas. Each mile of this sophisticated pipeline required an astonishing 46 tons of lead, along with substantial amounts of steel tape and armored wire. The manufacturing process for the HAIS pipeline was a marvel of wartime industrial mobilization. British factories, many of which had been converted from civilian to military production, worked around the clock to produce the components. Women played a crucial role in this effort, taking on industrial jobs traditionally performed by men who had been called up for military service. In factories across Britain, these women meticulously assembled the layers of the HAIS pipeline, their hands crafting a weapon as vital to Allied victory as any tank or aircraft. While HAIS offered excellent performance, it had one significant drawback. It depended heavily on lead, a material in critically short supply during wartime. This limitation led to the development of a second pipeline design called HAML, named after its inventors H.A. Hammock and Bernard J. Ellis, chief engineers from Iraq Petroleum Company and Burma Oil Company, respectively. The HAML pipeline used mild steel instead of lead, making it more economical and easier to produce in quantity. It consisted of 3.5-inch diameter steel pipes with 0.212-inch walls, manufactured in 30-foot sections that could be welded together. A special broaching tool was designed to remove the metal swarf that typically formed around welds, ensuring a smooth interior surface for optimal fuel flow. Testing began in May 1942 across the Medway River in Britain, followed by trials in the Firth of Clyde off Scotland in June. Engineers conducted these tests under the guise of routine maintenance of submarine cables, maintaining the veil of secrecy that surrounded the entire operation. The results were promising enough to move forward with full production. Siemens Brothers manufactured the HHIS cables both in the United Kingdom and the United States, while the Hamel pipes were produced entirely within Britain. By 1943, British factories were churning out an impressive 16 kilometers, about 10 miles, of pipeline every day, building up a stockpile of over 550 kilometers, 340 miles, for the eventual channel crossing. Rigorous quality control was essential. Each section of pipeline had to withstand enormous pressures, up to 700 pounds per square inch, while exposed to the corrosive effects of seawater. A single failure could compromise the entire operation, so engineers subjected sample sections to punishing stress tests, simulating the conditions they would face at the bottom of the channel. Only those that passed these grueling trials were approved for use in the actual deployment. The challenge of how to lay these pipelines across the channel still remained. This is where the strange, drum-like structures came into play. Engineers developed massive spools called conundrums, a play on words suggesting the challenging puzzle they represented. These enormous cylindrical drums, 30 feet in diameter and weighing 250 tons each, could hold miles of coiled pipeline. The flexible Hyes pipes were wound around these drums, which would then be towed across the channel between England and France. As the drum rotated, the pipeline would unwind and sink to the seabed. The Hamel pipes, being less flexible, required a different approach. They were wound onto the drums in shorter sections and deployed with HAIS pipe segments at each end to provide the necessary flexibility for the shore connections. The engineering team conducted a general rehearsal of the PLUTO installation in 1943, connecting the localities of Swansea and Watermouth, a distance of about 50 kilometers. This practice run allowed them to refine their techniques and identify potential problems before the actual channel crossing. It was a vital learning experience, revealing issues with pipe handling, deployment rates, and connection procedures that could be addressed before the real operation began. To carry out the actual pipeline laying, the Royal Navy modified several vessels, including HMS Holdfast, HMS Sancroft, and HMS Latimer. These ships were specially adapted to handle the conundrums and their precious cargo of pipeline. A flotilla dedicated to Operation Pluto was assembled, consisting of about 100 officers and 1,000 sailors, technicians, and workers under the command of Captain J.F. Hutchings. Their base of operations was primarily in Southampton, away from the prying eyes of German reconnaissance. Captain Hutchings faced the daunting task of coordinating this unprecedented operation while maintaining absolute secrecy. A veteran naval officer with experience in submarine warfare, Hutchings brought a steady hand and meticulous attention to detail to his command. He would need both qualities in abundance as his team prepared to lay miles of pipeline across one of the busiest and most heavily patrolled waterways in the world. In the spring of 1943, the Petroleum Warfare Department selected two primary sites for pumping stations on the English coast: Sandown on the Isle of Wight and Dungeness on the Kent coast. These locations would serve as the starting points for the two main pipeline routes across the Channel. The Sandown route would connect to Cherbourg in Normandy, covering a distance of about 70 nautical miles. This route was codenamed Bambi, continuing the Disney theme. The second route from Dungeness would run to Boulogne in the Pas-de-Calais region of France, spanning approximately 30 nautical miles. This shorter route was given the codename Dumbo. Secrecy was paramount. Construction at these coastal sites was carried out at night, with equipment transported under tarpaulins to avoid detection. The pumping stations and storage tanks were ingeniously camouflaged to blend into the surrounding landscape. Some were disguised as seaside villas or cottages, others as old forts or amusement parks. At Dungeness and Greatstone, where the Pluto pumping installations were within range of German guns in France, the disguise was particularly crucial. In total, 27 seaside bungalows and houses in these areas were adapted or constructed to conceal the pumping operations. Some buildings were made to look like ice cream shops or ordinary garages, complete with fake entrances and carefully maintained appearances to fool any German reconnaissance flights. The level of detail in these disguises was extraordinary. At one location, engineers created a false storefront for an ice cream parlor, complete with menus and serving counters. Behind this innocent facade, powerful pumps capable of pushing fuel under extreme pressure waited silently for deployment. At another site, a garage was established where military vehicles disguised as civilian trucks would regularly arrive and depart, maintaining the illusion of ordinary commercial activity while actually delivering vital equipment for the Pluto operation. Local residents near these installations were kept in the dark about their true purpose. Security was so tight that even workers at the sites were often unaware of the bigger picture, knowing only their specific tasks, without understanding how they fit into the overall operation. This compartmentalization of information was a standard security practice, ensuring that no individual could compromise the entire project if captured or interrogated by enemy agents. The deception extended beyond the coastal installations. As part of Operation Fortitude, the broader Allied deception plan surrounding D-Day, a fake oil dock was created at Dover. This elaborate decoy, designed by architect Basil Spence, spanned 3 acres and was constructed from camouflaged scaffolding, fiberboard, and old sewage pipe. It included fake versions of pipelines, storage tanks, jetties, vehicle parks, and anti-aircraft emplacements. Wind machines created clouds of dust to simulate activity, while at night, the entire installation was obscured by a smoke screen. The site was even guarded by military police to enhance its credibility. This theatrical production had one purpose: to distract German intelligence from the real Pluto operations nearby. Operation Fortitude represented one of the most elaborate deception campaigns in military history. It created the illusion of a massive army group poised to strike at the Pas de Calais, diverting German attention and resources away from Normandy. The fake oil installations at Dover played into this broader deception, suggesting preparations for a crossing at the narrowest part of the channel. Meanwhile, the real Pluto preparations continued elsewhere, hidden beneath this layer of strategic misdirection. Behind this veil of secrecy, a complex network of pipelines was being built across Britain to feed the Channel crossing. Fuel would be transported from the safer regions of the United Kingdom, primarily Liverpool and Bristol, through a system known as the Government Pipeline Storage System, GPSS. This network of pipes would carry the fuel to the southeast coast, where it would connect to the Pluto pipelines crossing the Channel. The entire operation was a masterpiece of engineering and logistics, involving thousands of workers across multiple industries, all sworn to secrecy about their part in this critical war effort. The GPSS itself was an impressive achievement, consisting of approximately 1,000 miles of pipeline linking the major ports and refineries of western England to the vulnerable southeastern coast. Construction had begun in 1941 in response to the German bombing of coastal oil installations, and the system had proven its worth by reducing the need for vulnerable tanker traffic along Britain's eastern and southern shores. Now it would serve as the vital link between Britain's fuel reserves and the Pluto system, ensuring a continuous flow of petroleum to the invasion forces. As D-Day approached, anticipation grew among those privy to the Pluto plans. The success of the invasion and subsequent campaign would depend significantly on maintaining a steady flow of fuel to the advancing Allied forces. The Pluto team knew they had to be ready to deploy their pipelines as soon as the beachheads in Normandy were secure enough to establish the receiving end of the system. The invasion date was set for June 6, 1944, but PLUTO would have to wait until the military situation stabilized before pipeline laying could begin. The D-Day landings succeeded, but the battle for Normandy proved more protracted than initially hoped. The original PLUTO timeline had assumed that Cherbourg Harbor would be captured intact within 8 days of the invasion. In reality, the port didn't fall to Allied forces until June 27th, and even then, retreating German forces had extensively sabotaged the harbor facilities. This delay, combined with the continuing struggle to break out of the Normandy beachhead, pushed back the PLUTO deployment schedule. The weeks following D-Day saw intense fighting as Allied forces sought to expand their foothold in Normandy. German resistance was fierce, with Field Marshal Rommel throwing in everything he had to drive the invaders back into the sea. The crucial port of Cherbourg, designated as the terminus for the Bambi pipeline route, was heavily defended. American forces of the 7 Corps under General J. Lawton Collins had to fight their way up the Cotentin Peninsula and then engage in house-to-house combat to secure the city. When they finally prevailed on June 27th, they found that German demolition teams had thoroughly wrecked the port facilities, rendering them temporarily useless for supply operations. During this period, Allied forces relied on makeshift harbor facilities and the ingenious Mulberry artificial harbors to bring in supplies. Fuel arrived in ships, was transferred to smaller vessels or floating pipelines for transport to shore, and then moved by truck to forward positions. This system was vulnerable and inefficient, but it kept the invasion forces supplied during the critical early weeks. Meanwhile, the PLUTO teams waited impatiently for their chance to deploy their underwater pipelines and revolutionize the fuel supply chain. Finally, on August 12, 1944, more than 2 months after D-Day, Operation PLUTO formally began. HMS Latimer attempted to lay the first TAIS pipeline from the Isle of Wight to Cherbourg. The ship completed the task in just 10 hours, an impressive feat. But disaster struck when an escorting destroyer accidentally caught the pipeline with its anchor, damaging it beyond repair. 2 days later, HMS Sancroft tried again, but this attempt also failed when the pipe became wrapped around the propeller of the support ship HMS Algerian. These initial setbacks were demoralizing for the PLUTO team, who had worked for years to prepare for this moment. Captain Hutchings later recalled the tense atmosphere aboard HMS Sancroft during the second attempt. "We had come so far, overcome so many obstacles, that to fail at this critical juncture seemed unthinkable." Yet the channel was proving even more challenging than we had anticipated. The currents, the weather, the technical difficulties of laying pipe at sea all conspired against us, but we were determined to persevere. Undeterred, the PLUTO team switched to trying the Hamel pipe instead, but encountered an unexpected obstacle. Tons of barnacles had attached themselves to the bottom of the conundrum, preventing it from rotating properly. After scraping off the barnacles, another attempt was made, but the pipeline broke about 29 nautical miles into the crossing. These initial failures highlighted the extreme challenges of the operation. As Sir Donald Banks, Director General of the Petroleum Warfare Department, later wrote, "The technique of cable laying had been mastered, but we were not yet sufficiently versed in the practice of connecting the shore ends, nor in effecting repairs to the undersea leaks which were caused fairly close inshore through these faulty concluding operations." The difficulties faced by the PLUTO team were not just technical, but operational as well. The English Channel remained a contested waterway despite Allied air superiority. German E-boats, fast attack craft, continued to patrol, posing a threat to the pipeline laying operations. Luftwaffe reconnaissance flights, though increasingly rare due to Allied air dominance, could still potentially spot and report unusual activity. The pipeline-laying ships had to maintain radio silence whenever possible and operate with minimal escort to avoid drawing attention to their activities. The Nazi intelligence services, meanwhile, remained oblivious to these activities in the Channel. German reconnaissance planes might have observed unusual shipping movements, but the true purpose of these operations was obscured by the elaborate deception measures. The Germans were focused on the more visible aspects of the Allied advance through Normandy and the conventional tanker traffic supplying the invasion forces. The idea of an underwater pipeline was so audacious, so beyond conventional thinking, that it simply wasn't considered as a possibility by German analysts. This blind spot in German intelligence wasn't entirely surprising. Throughout the war, Nazi military thinking had often been characterized by a strange mix of technological innovation and conservative doctrine. While German engineers produced revolutionary weapons like the V-1 flying bomb and V-2 rocket, their military leadership sometimes failed to appreciate or anticipate the technological innovations of their enemies. The concept of an underwater petroleum pipeline spanning the English Channel was simply outside their frame of reference, making it the perfect secret weapon, one that the enemy couldn't counter because they couldn't imagine it existed. Perseverance finally paid off for the PLUTO team on September 22, 1944, when a Hayes cable was successfully laid and began delivering fuel at a rate of 56,000 imperial gallons, about 254,000 liters per day. A week later, on September 29th, HMS Conundrum 2 successfully installed a Hamel cable as well. However, on October 3rd, when engineers attempted to increase the pressure from 50 to 70 bars to boost fuel flow, both pipelines failed, the HIs due to a faulty coupling, and the Hamel from an undetermined cause. Despite these continued challenges, the PLUTO team had proven their concept worked. The pipeline could be laid successfully across the channel, and it could deliver significant quantities of fuel directly to the Allied forces in France. Now it was a matter of refining the techniques, addressing the weak points, and establishing a reliable pipeline system that could support the ongoing Allied advance across Europe. These setbacks, with the Bambi route from the Isle of Wight to Cherbourg, led to a shift in focus to the alternative Dumbo route from Dungeness to Boulogne. This shorter crossing offered better prospects for success, though it required adjustments to the original plan. Instead of terminating at Ambleteuse as initially intended, the pipelines were directed to Boulogne, since the beaches at Ambleteuse were heavily mined. Although this involved a longer distance and a more difficult approach, cable-laying techniques had improved through the painful lessons of earlier failures. The military situation had changed dramatically by October 1944. The Allied breakout from Normandy, followed by the rapid advance across France and into Belgium, had transformed the strategic landscape. Paris had been liberated on August 25th, and Brussels fell to Allied forces on September 3rd. By late September, Allied troops were fighting on German soil in the Aachen area. This advance had opened up new ports closer to the front lines, including Boulogne, which was captured by Canadian forces on September 22nd. The Dumbo route now made more strategic sense than ever, providing a shorter pipeline connection to a port that was better positioned to support the continuing Allied push eastward. On October 26, 1944, HMS Sancroft successfully laid a Hayes pipeline from Dungeness to Boulogne, which began pumping fuel immediately and continued operating until the end of the war. The Hamel pipe still presented challenges, but engineers found a solution by using sections of HIS pipe at each end to provide the necessary flexibility for the shore connections. As Boulogne's railway facilities were poor, the pipeline was extended overland to Calais, which offered better transport connections for distributing the fuel to Allied forces pushing eastward. The successful establishment of the Dumbo pipeline system marked a turning point for Operation PLUTO. After months of technical problems and frustrating setbacks, the underwater fuel highway was finally operational. The persistence, ingenuity, and dedication of the PLUTO team had overcome seemingly insurmountable challenges to create a lifeline of petroleum that would help drive the Allied armies to victory. The Dumbo pipeline system proved far more successful than its Bambi counterpart. By December 1944, 9 3-inch and 2 2-inch Hamel pipelines, along with 4 3-inch and 2 2-inch Chase pipelines, A total of 17 pipelines had been laid across the channel. Together, they were delivering 2,300 tons of fuel per day to support the Allied advance. Remarkably, not one of the HAI's pipelines failed during operation, while the Hamel lines required repairs only every 52 to 112 days on average. This success came at a crucial moment in the war. In December 1944, Hitler launched his last major counteroffensive in the West, the Battle of the Bulge. German forces, spearheaded by panzer divisions, smashed through the Allied lines in the Ardennes forest, creating a bulge in the front. This desperate gamble was aimed at splitting the Allied armies and capturing the vital port of Antwerp. One of the factors that ultimately doomed the German offensive was their chronic fuel shortage. German tanks literally ran out of gas and had to be abandoned as the offensive ground to a halt. Meanwhile, thanks in part to the PLUTO pipeline system, Allied forces had sufficient fuel reserves to contain and eventually repel the German attack. All of this occurred completely unbeknownst to the Germans. As Allied forces pushed deeper into France and the Low Countries, Nazi intelligence remained focused on traditional supply methods. They tracked ship movements, bombed ports, and attempted to disrupt conventional fuel shipments, never realizing that an increasing proportion of Allied fuel was flowing silently beneath the waves, immune to their attacks. The camouflaged pumping stations on both sides of the channel continued their work, their true purpose hidden behind innocent facades. The success of PLUTO rested not just on the pipeline technology itself, but on the comprehensive system that supported it. On the British side, the pipelines connected to the GPSS network, which in turn linked to the major oil storage facilities at Avonmouth near Bristol and other locations. On the French side, the pipelines fed into a distribution network that grew along with the Allied advance. Receiving stations, booster pumps, and storage tanks were established at strategic locations, often disguised as ordinary buildings or constructed within existing structures to maintain secrecy. By January 1945, the PLUTO pipelines were transporting 305 tons of fuel across the English Channel daily. This increased dramatically to 348 tons in March, and by May 1945, as the war in Europe drew to a close, PLUTO was delivering an impressive 4,000 tons of fuel daily. Over the entire course of its operation from August 1944 to May 1945, PLUTO delivered approximately 172 million gallons, or about 781,000 cubic meters, of fuel to Allied forces in Europe. This massive quantity flowed literally beneath the feet of German forces, who never discovered the source of their enemies' seemingly limitless fuel supply. The men and women who operated the PLUTO system worked in conditions of extraordinary secrecy. Many were civilians who had been drafted into this classified operation, sworn to absolute silence about their work. They lived in isolated compounds, often cut off from the outside world for weeks at a time. The pressure was immense. They knew that the lives of thousands of soldiers and the success of the Allied campaign depended on their maintaining both the operation of the pipeline and the secrecy surrounding it. One veteran of the PLUTO operation later recalled, "We knew we were doing something important, something that could help win the war, but we couldn't talk about it with anyone, not our families, not our friends, not even amongst ourselves outside of the secure areas. It was a strange existence, living with this tremendous secret, knowing that a careless word could compromise everything we were working for. But there was also a certain pride in it, in knowing that we were part of something truly remarkable, something that was making history, even if nobody knew about it at the time." The success of PLUTO represented more than just a technical achievement. It embodied the innovative spirit that characterized the Allied war effort. When faced with seemingly insurmountable challenges, engineers and military planners found creative solutions that their enemies could not anticipate. General Dwight D. Eisenhower, the supreme Allied commander, later acknowledged the significance of the operation when he declared that it was second in daring only to the Mulberry Harbors. the prefabricated ports towed across the channel to support the D-Day landings. The PLUTO pipelines contributed significantly to the final phase of the war in Europe. As Allied armies pushed into Germany in early 1945, the demand for fuel continued to grow. The rapid advance meant that supply lines were stretched thin, making the direct pipeline connection from Britain all the more valuable. Without the steady flow of petroleum through the underwater pipeline network, the Allied drive into Germany might have been delayed, potentially prolonging the war and costing additional lives. As Allied forces closed in on Berlin from east and west, German resistance grew increasingly desperate, but ultimately futile. With their own fuel supplies nearly exhausted, their air power decimated, and their industrial capacity crippled by strategic bombing, the Third Reich was running on empty. Meanwhile, the Allied war machine, well supplied with fuel from various sources, including the PLUTO pipelines, continued its relentless advance. On May 7, 1945, Germany surrendered unconditionally, bringing the war in Europe to an end. As the war in Europe ended, the German High Command was finally briefed on Operation PLUTO during debriefings with Allied officials. The Nazi officers were reportedly astonished that such an elaborate underwater fuel delivery system had been constructed and operated right under their noses without detection. This revelation stood as a testament not only to the engineering prowess of the Allies, but also to the effectiveness of their security and deception measures. Admiral Karl Dönitz, who briefly succeeded Hitler as head of state in the final days of the Reich, was particularly struck by the PLUTO revelation. As a submarine commander and later head of the German Navy, Dönitz had devoted considerable resources to disrupting Allied supply lines at sea. The existence of an underwater pipeline that had completely evaded German detection represented a profound intelligence failure and a remarkable Allied achievement. Dönitz reportedly remarked that had the Germans known about PLUTO, they would have concentrated all available resources on locating and destroying the pipelines, recognizing their critical importance to the Allied war effort. The PLUTO system continued pumping fuel until August 7, 1945, when it was finally shut down to save manpower. By that time, conventional supply routes had been fully established, and the emergency measure that PLUTO represented was no longer necessary. The operation was officially disbanded on August 31, 1945, and the Petroleum Warfare Department was wound up on March 31, 1946. In the aftermath of the war, the pipelines didn't simply disappear. In September 1946, a recovery operation began using HMS Latimer, renamed Empire Ridley after the war, HMS Holdfast, renamed Empire Taw, Empire Tignes, and Redeemer. These vessels recovered most of the redundant cables, though about 10% of the pipelines were never retrieved and remain on the channel floor to this day. Interestingly, the sale of the recovered materials, particularly the lead and steel, generated more profit than expected and largely covered the costs of the recovery operation. The legacy of PLUTO extended far beyond the war years. The technology developed for the underwater pipelines found new applications in peacetime, particularly in the emerging offshore oil industry. The techniques for manufacturing, laying, and maintaining underwater pipelines that had been pioneered under the pressures of war would later be adapted for commercial use in the North Sea oil fields and beyond. In this way, PLUTO contributed not only to winning the war, but also to post-war economic development. The impact of PLUTO extended far beyond its immediate military application. The technological innovations developed for this wartime emergency laid the groundwork for advances in peacetime undersea pipeline construction. Modern offshore oil and gas installations owe much to the pioneering work of the PLUTO engineers. The experience gained in designing flexible pipelines that could withstand harsh marine environments, the techniques for laying pipes on the seabed, and the methods for monitoring and maintaining underwater pipelines all found applications in the post-war petroleum industry. In the decades following World War II, as offshore oil exploration and production expanded globally, the lessons learned from PLUTO proved invaluable. The North Sea oil boom of the 1970s and 1980s, which transformed Britain's economy, relied on underwater pipeline technology that could trace its lineage back to the wartime emergency project. Engineers who had worked on PLUTO went on to contribute their expertise to this new chapter in energy production, creating a direct link between the secretive wartime operation and the modern energy infrastructure that powers our world today. The human stories behind PLUTO are equally compelling. Thousands of individuals, engineers, oil company workers, military personnel, and civilian contractors contributed to its success while maintaining absolute secrecy about their work. Many went to their graves never having spoken publicly about their role in this classified operation. Captain John Fenwick Hutchings, who commanded the PLUTO flotilla, was awarded the CBE, Commander of the British Empire, for his leadership. Arthur Hartley, the visionary engineer who first proposed the submarine pipeline concept, received a tax-free payment of $9,000 from the Royal Commission on awards to inventors after the war, recognizing his crucial contribution to the Allied victory. Bernard J. Ellis, who developed the Hamel pipe design, was awarded $5,000, while smaller sums went to other key contributors, such as M.K. Purvis, the designer of the conundrum, who received $85, and A.E. Price, who designed the wedge-gripping device used to fix the pipeline near the shore, who was given $250. These financial rewards, though modest by modern standards, acknowledged the vital role these innovations played in sustaining the Allied advance across Europe. For many of the rank-and-file workers on the PLUTO project, recognition came much later, if at all. The classified nature of the operation meant that many could not include it on their resumes or discuss it during job interviews after the war. It was only decades later, as documents were declassified and the full story of PLUTO emerged, that these individuals could finally receive public acknowledgement for their contributions to this remarkable achievement. One such individual was Joan Welch, a young woman who worked as a technical draftsperson on the PLUTO project. Like many women during the war, she had stepped into a role traditionally held by men, bringing her keen intellect and attention to detail to the exacting work of creating technical drawings for the pipeline components. After the war, she returned to civilian life, unable to speak about her wartime service until the 1970s, when the full story of PLUTO was finally made public. Her experience was typical of many who served in classified operations, their contributions remaining hidden from history for decades. The story of Operation PLUTO embodies the qualities that ultimately led to Allied victory in World War II. Innovation in the face of seemingly impossible challenges, meticulous planning and execution, effective security and deception, and dogged perseverance despite initial failures. While more celebrated aspects of the war, the dramatic tank battles, strategic bombing campaigns, and infantry assaults, captured greater public attention, it was often these behind-the-scenes logistical triumphs that made the difference between victory and defeat. The fact that Nazi intelligence never discovered PLUTO speaks volumes about the effectiveness of Allied counterintelligence and the comprehensive nature of the deception measures employed. German reconnaissance might observe unusual activities in the Channel or strange structures along the British coast, but these observations were successfully masked within the broader context of war operations or dismissed as unimportant anomalies. The Germans were looking for conventional threats and supply methods. They simply weren't primed to recognize the unconventional solution the Allies had devised. This blind spot in German intelligence wasn't merely a matter of oversight. It reflected a broader failure of imagination, an inability to conceive of the technical innovations their adversaries might develop. Throughout the war, Allied forces repeatedly surprised the Germans with unexpected technologies and tactics, from the use of electronic countermeasures to confused German radar to the development of specialized armored vehicles for the D-Day landings. PLUTO stands as one of the most successful examples of this pattern, remaining completely unknown to the enemy until after hostilities had ceased. The strategic implications of PLUTO extended beyond the immediate military benefits. By providing a secure, weather-independent means of delivering fuel to the front lines, the pipeline system reduced the Allies' vulnerability to German countermeasures. It freed up shipping for other purposes, reduced the risk to sailors and dock workers who would otherwise have been handling fuel in exposed positions, and ensured a steady supply regardless of weather conditions or enemy activity. This reliability gave Allied commanders greater confidence in planning offensive operations, knowing that their fuel supplies would not be interrupted at a critical moment. The legacies of PLUTO are many and varied. In technical terms, it advanced the field of submarine pipeline construction by decades. The HAI's and Hamel designs influenced post-war offshore oil infrastructure development, particularly in the North Sea oil fields that would become so crucial to Britain's economy in later decades. The concept of using flexible pipes wound on drums for deployment at sea is still employed in modern offshore operations, albeit with far more sophisticated materials and techniques. In military terms, PLUTO demonstrated the critical importance of fuel supply in modern warfare and pioneered new approaches to securing that supply in hostile environments. Future military planners would incorporate these lessons into their logistical strategies, recognizing that control of energy resources and their transportation could be as decisive as traditional combat operations. In the realms of intelligence and counterintelligence, PLUTO stands as a case study in effective operational security. The comprehensive deception measures, compartmentalized information, and strict need-to-know protocols ensured that one of the war's most ambitious engineering projects remained hidden from enemy detection. These principles would influence Cold War intelligence practices and continue to inform modern military security procedures. Perhaps most significantly, PLUTO exemplifies the spirit of wartime collaboration between civilian industry, scientific researchers, and military forces. Oil companies, engineering firms, government departments, and armed services personnel work together seamlessly, setting aside commercial rivalries and institutional boundaries in service of a common goal. This model of cooperation would be emulated in later national endeavors, from space programs to large-scale infrastructure projects. The story of PLUTO also highlights the critical role of individual initiative and leadership in wartime innovation. From Lord Mountbatten's initial question about the possibility of an underwater pipeline to Arthur Hartley's creative adaptation of submarine cable technology, from Captain Hutchings's steady leadership of the naval operation to the countless engineers who solved specific technical problems, PLUTO was made possible by individuals willing to think outside conventional boundaries and persevere in the face of skepticism and setbacks. Today, physical remnants of Operation PLUTO can still be found. On Romney Marsh in Kent, concrete casings that once protected the pipeline where it crossed water drainage ditches can be spotted by observant visitors. In Greatstone, several of the PLUTO bungalows that housed pumping equipment still stand, though most have been modified over the decades. At Dungeness, PLUTO Cottage, once a disguised pumping station, served for years as a bed and breakfast before becoming a private residence. These humble structures give little indication of their historic significance, which is perhaps fitting for an operation defined by its invisibility. Beneath the waves of the English Channel, sections of the original pipelines lie on the seabed, slowly being reclaimed by marine life. Approximately 10% of the PLUTO network was never recovered, providing an underwater monument to this engineering marvel. Occasionally, storms or seabed activities reveal segments of these historic pipes, tangible connections to one of World War II's most closely guarded secrets. The PLUTO story has gradually emerged from the shadows of wartime secrecy. In the immediate post-war years, security considerations prevented full disclosure of the operation's details. Documents related to PLUTO were sealed in the Public Record Office for 30 years, like many other sensitive wartime records. It was only in the 1970s that the complete story began to emerge through declassified documents and the memoirs of participants. Today, PLUTO is recognized as one of the most impressive engineering achievements of World War II, though it still remains less well known than other aspects of the conflict. This relative obscurity is, in some ways, a continuation of PLUTO's wartime role, operating effectively in the background, essential but unheralded, its impact far greater than its public profile would suggest. For those who study military logistics or engineering history, however, PLUTO stands as a testament to human ingenuity and determination. It demonstrates how innovative thinking and technological adaptation can overcome seemingly insurmountable challenges, and how careful security measures can keep even massive engineering projects hidden from enemy detection. The story of PLUTO reminds us that wars are not won solely on the battlefield. Victory often depends on innovative solutions to logistical challenges, on the ability to anticipate and meet the material needs of fighting forces. As the Allied armies pushed across France, Belgium, the Netherlands, and what eventually entered Germany itself, they did so with the confidence that fuel, the lifeblood of modern warfare, would continue to flow. That confidence was well placed thanks to the invisible network of pipelines that had been laid across the Channel floor, unseen and unsuspected by the enemy. In the final analysis, Operation PLUTO stands as a testament to human ingenuity, to the power of creative thinking in overcoming seemingly insurmountable obstacles. It demonstrates how, in times of greatest need, individuals from diverse backgrounds can come together to achieve what previously seemed impossible. And it reminds us that sometimes the most effective weapons in war are those the enemy never sees coming, or, in the case of PLUTO, never sees at all. The underwater pipelines that fueled the Allied advance across Europe represent one of history's most successful marriages of technical innovation and strategic deception. While Nazi officers scrutinized the skies for Allied bombers and scanned the horizon for supply ships, the real threat to their defenses lay hidden beneath the waves, pumping victory gallon by gallon to the armies that would ultimately defeat them. In war, as in life, it is often what we fail to see that proves most decisive. For the Germans, PLUTO remained invisible until it was too late, a secret weapon that helped fuel the liberation of Europe and hasten the end of Hitler's Third Reich.